Okay, so after a detour involving a discussion about matrices, the rank of a matrix, determinants of properties and so on. Now we return to our the abstract linear vector space, and we define some very important properties of a linear vector space, right? So there is the notion of a span, the notion of a basis, and dimension of a linear vector space, right? So these are the topics which will be covered in this lecture. Okay, so if you are given a bunch of vectors, so the span of this set of vectors is simply all possible vectors that can be produced as a linear combination of these vectors, right? So you say that a set of vectors spans a space if all the vectors in this space can be written as linear combinations of the spanning set. Or you might also think of this, the span of a given set of vectors is a space, right? You say that a set of vectors spans a space if every vector in that space can be written as the linear combination of a set of vectors, and alternately the span of a set of vectors is the space which is created by coming up with all linear combinations of vectors drawn from that set, right? So that's the notion of a span. Now for example, right, if you take the set Ex and Ey, two-dimensional vectors, so the unit vector along the x direction, the unit vector along the y direction, the span of just these two vectors is actually the infinite two-dimensional plane. So every vector in 2D can be written as ax times Ex plus ay times Ey. So likewise, the span of the set Ex and Ex plus y, Ey is also the two-dimensional plane, right? So these two are not orthogonal, but they are just these two vectors are enough to generate for you the whole two-dimensional plane. And likewise, in fact, you may put in more vectors drawn from the two-dimensional plane. For example, you could consider Ex, Ey and Ex plus Ey, but every vector that is obtained as a linear combination of these three vectors is still going to be just the two-dimensional plane. You are not going to get any vector which lies outside of the 2D plane. So in fact, you can put more vectors into this set, which as long as they're all vectors within the two-dimensional plane, the span of this set that you're going to come up with is still going to be the two-dimensional plane, right? So you see that there is, on the one hand, there is the notion of a span of a set, and then you might start thinking, is there some minimal set, right? It seems like there is a lot of redundancy in these kinds of sets that you may come up with, right? So that's where the notion of the basis comes in, right? So the minimal set which can generate for you the whole space is what is the idea of a basis, right? So here we have to bring in not only the idea of a span, but also that of linear independence, right? So if you impose also linear independence on these vectors, you have a bunch of vectors which are all linearly independent, and then if you take the span of such a set and you create a space, right? So this set is going to form a basis for this space. So another way of thinking of this is you have a space already, a vector space is given. Now a basis for this vector space is any set of vectors which are all which have to satisfy two properties. One is they have to be mutually linearly independent, right? And they have to span the space. So which means basically that every vector in that space should be representable as a linear combination of the vectors from this set that you have taken, and then it becomes a basis. Right? So an example here is Ex and Ey. Again we look at the same three examples we considered with regard to the span. Ex and Ey, that's going to be a basis. Ex and Ex plus Ey is also a basis, right? Although they are not orthogonal to each other, and so Ex and Ey, we have been using Ex and Ey as a basis all along, right? Without perhaps thinking of them as a basis, because it's a very convenient basis to work with. Ex and Ex plus Ey perhaps is not such a convenient basis, but it's still a basis, all right? Because any vector in the two-dimensional space can be written as a linear combination of Ex and Ex plus Ey, right? This is something that you can check, right? In fact, we already showed this for arbitrary vectors. If you have any two arbitrary vectors A and B, right, in some plane, any other vector can be written as a linear combination of A and B. We showed this, using the cross product of these vectors, right, which uniquely defines the direction perpendicular to the plane. Therefore, the plane is defined, and so any other vector can be obtained in terms of A and B, right? So here Ex and Ex plus y, for sure they will form a basis, but the set Ex, Ey and Ex plus Ey is not a basis, right? The reason is there is redundancy here, right? So the basis in some sense is a very compact set, right? It does not have any more information than necessary, and it cannot have less information than necessary. It needs to have exactly the relevant amount of information, right? So what is that relevant? How much is that relevant information? There is something which seems to be conserved, right? You can have many different kinds of bases, but apparently all of them are able to generate for you the whole space in a very so that there is also no wastage. There is no unnecessary vectors here. So what is this thing that is getting conserved? And that is the idea of the dimension of a vector space. So the dimension of a vector space is a well-defined object, right? It is it's just equal to the number of vectors in any basis, right? As you have seen, you can think of many different ways. I could have thought of it as Ex and Ex plus Ey, or I could have created a basis made up of Ey and Ex plus Ey, or Ey and 3 times Ex plus 4 times Ey. I can think of many different ways of constructing a basis, right? But one thing for sure is, if you're looking at this 2D space, any basis is going to have exactly 2 elements, right? And so that's the idea of the dimension of a vector space, right? So there you go. So once again, if you look at these examples, Ex and Ey, and Ex and Ex plus Ey, or you can think of Ex plus Ey and Ex minus Ey, all of these are bases. You can construct bases in zillions of different ways. All of them will have exactly 2 elements as far as this vector space of 2-dimensional vectors is concerned. So the dimension of this vector space is 2. Now, in all our discussions, so you see that although the dimension of your space is just 2, right? It's finite, and in fact, it's a very small number, it's just 2. And yet, the number of vectors in this space is actually infinite, right? You can use a relatively small number of vectors and create infinitely many vectors, right? So although the number of vectors in your set is an infinite set, but it has a finite dimension, right? So in our discussion, we are going to restrict ourselves to finite dimensional vector spaces. So of course, as you might guess, there are also infinite dimensional vector spaces, and so there one has to be more careful, right? So with regard to some of the results that we prove for example, right, if you take all complex numbers, we have seen that it's a vector space. You can, if you add any 2 complex numbers, you're going to get another complex number, and so on, right? So you can think of many infinite dimensional vector spaces as examples, but we will, for all the theorems or results that we are going to describe, we are going to stick to finite dimensional vector spaces. Okay, so let us look at some important consequences of just this set of definitions that we have made: span, basis, and dimension, right? So one is the decomposition of, so we have said that for a set to be a basis, it must be able to represent any vector in that space as a linear combination of those vectors from that basis. Now already we can show that the decomposition of any vector in terms of the vectors of a basis not only exists, but it is unique. That it exists already has been said within the definition, but now we can show that it is unique, and this in fact follows from the linear independence of the vectors. So let's look at this argument. If you want to pause the video and try to work out the argument for yourself, please feel free to do so. So here is the argument. So let E1, E2, E3, so on, En be a basis for an n-dimensional vector space V. Now consider any vector x, which is an element of this space. Now the basis must span this space, right? Otherwise you wouldn't call it a basis. Therefore, you will be able to find some coefficients, alpha 1, alpha 2, alpha n, these scalars, such that you'll be able to write, expand your vector x as alpha 1 E1 plus alpha 2 E2, so on, plus alpha n En. Now, but suppose this is not unique. Suppose your friend tells you that you have he has found another way of doing this expansion. So there is another set of coefficients, beta 1, beta 2, all the way up to beta n, x, where you write x as beta 1 e1 plus beta 2 e2 all the way up to summation beta n en. Now we'll show that this immediately implies that alpha 1 is equal to beta 1, alpha 2 equal to beta 2, and so on, all the way up to alpha n is equal to beta n, which means that there's a unique decomposition. So how does this come about? So we just simply subtract these two. You have an equation for x and you have another equation for x. So if you subtract these two, you're going to get 0, the 0 vector, which you can think of it as a 0 as well, right? So it is, so on the right hand side you have the 0 vector, and on the left hand side you have alpha 1 minus beta 1 times e1 plus alpha 2 minus beta 2 times e2, so on all the way up to alpha n minus beta n en. Now, so but these vectors e1, e2, e3, so on must be linearly independent, right? So if they must be linearly independent, the definition of linear independence is that you will never be able to find some set of coefficients which are not all 0, such that the set of coefficients times the various elements of the various vectors involved here, summation over all of them is equal to 0, right? That's precisely what we have here. We seem to have found a set of coefficients alpha 1 minus beta 1, alpha 2 minus beta 2, so on all the way up to alpha n minus beta n, such that if we tag these coefficients along with them, with the vectors, and add them, we are getting 0, right? If these vectors have to be linearly independent, it immediately implies that each of these coefficients, that is alpha 1 minus beta 1 is equal to 0, alpha 2 minus beta 2 equal to 0, and all the way up to alpha n minus beta n is equal to 0. Therefore, the decomposition of this vector x must be unique, right? So this follows directly from the linear independence of the vectors of a basis, right? So next we have another result. This is a very beautiful result, right? So you have any set of n plus 1 vectors drawn from an n-dimensional vector space must be linearly dependent, right? So if you want to pause the video and try to work this out on your own, please do so. So this again will use some of the ideas from matrices that we worked on a few lectures ago. So let's look at the argument now. So you have a set of vectors v1, v2, vn, and also vn plus 1. You're given n plus 1 vectors. So the claim is that any n plus 1 vectors in an n-dimensional vector space necessarily must be linearly dependent, right? It's an n-dimensional space, so there is a basis of n vectors, e1, e2, all the way up to en, which are all linearly independent and which can span the space. So we should be able to write v1 as, expand v1 in terms of all these n vectors from the basis, v2 also in terms of the basis, v3, so on, all the way up to vn plus 1. So let's do that, and we have this matrix of coefficients alpha ij, right? I am writing vi as summation over j alpha ij ej, right? Now if we must show that these the vectors vi are linearly dependent, so that means we just need to find a set of coefficients eta 1, eta 2, all the way up to eta n plus 1, right? All of them non-zero, right? You cannot, if you have all of them 0, that's a trivial statement, right? You should be able to find a set of coefficients such that summation over I, eta I vi equal to 0, right? That's the condition for linear dependence. So let's see how to go about doing this. So this is the same as requiring, so in place of vi, I'll plug in this expansion in terms of the basis. So I have summation over I, eta I, summation over j, alpha ij, ej, right? So I goes from 1 to n plus 1, but j goes only from 1 to n, right? It's an n-dimensional space, so the number of vectors in the basis are going to be n. Now, but this is an expansion of the 0 vectors in terms of the given basis, right? And there is every vector has a unique expansion. Therefore, every the coefficient corresponding to every basis vector itself must be 0, right? So the uniqueness of this expansion forces each of the coefficients separately to be 0. So we have n homogeneous equations in n variables, right? So let's write that down. So we have, I'm collecting, first of all, I'm collecting the coefficients corresponding to E1. That will be alpha 1 1, eta 1 plus alpha 2 1, eta 2 all the way up to alpha n plus 1 comma 1, eta n plus 1 equal to 0. That's the first equation. The second equation will collect all the, the sum of the coefficients which correspond to the vector E2, and that also has to be 0. Third one, so on, all the way up to n plus 1. So we have eta 1, eta 2, eta n plus 1. We have n plus 1 unknowns and only n equations, and all of these are, have 0 on the right hand side. So this is a set of homogeneous equations. So we have seen that every homogeneous set of equations necessarily is consistent. So it for sure has at least the trivial solution. The trivial solution is, all the etas being 0. But that's not enough for us. We want to find a non-trivial solution, because if there is only a trivial solution, that means it is, we are not able to show the linear dependence, right? So, but the point is that since it's a homogeneous set, right, we can add one more equation for free. So, right, we have, right, I mean, it's a homogeneous set, and I can add one more equation for free and keep it a homogeneous equation, but now we have n plus 1 equations in n plus 1 variables, right? So you see that now we can bring in our determinant rule, right? Whenever you have a homogeneous system of equations, which is also square, right? So now we have converted this non-square system of homogeneous equations into a square system of homogeneous equations, for which the rule, we had a very simple rule. If you want to find a non-trivial solution for this, then all you need to show is, the requirement is that the determinant of the coefficient matrix must be 0. Now, which is evidently true in this case, right? So if you have forgotten this part, you should go back to the video from a few lectures ago and review it, right? If you have a square system of homogeneous equations and whose determinant of coefficients is 0, then for sure you have at least one non-trivial solution for the coefficient theta I. Thus the vectors v1, v2 all the way up to vn, n plus 1 are actually linearly dependent, right? So that's all, right? So we have managed to show that any arbitrary n plus 1 vectors in an n-dimensional space must be linearly dependent, right? So now, so in the light of this discussion, you can go back and think about the statement I made in the previous lecture, where I said that the number of linearly independent rows and the number of linearly independent columns of a matrix must be the same, right? So you might think that I can come up with construct a matrix with a very large number of columns, but just a much smaller number of rows, right? I don't know, like suppose you had 3 rows and 100 columns. So you might ask, how can I, the maximum number of linearly independent rows is just 3. So even though I have 100 columns, I will be able to get only 3 linear maximum, at most 3 linearly independent columns, right? So because the theorem of the equivalence of the row rank and the column rank will force this. And so in the light of this result that we have just proved, you might want to go back and think about this. So the moment you have, each of these columns, although you have a large number of columns, they have only 3 elements in each column. So therefore, the moment you have more than 3, there is going to be linear dependence, right? So there is a connection between this result and the result from the previous discussion, and I would like you to think about this. And before we end this lecture, there is one more result that I want to discuss. So which is that suppose you have an n-dimensional vector space, then any set of n linearly independent vectors constitutes a basis, right? So we saw for the 2-dimensional space, you could think of Ex and Ey as a basis, but Ex and Ex plus y is a basis. So Ex plus y, Ex minus y, any of these constituted a basis. So in fact, so you can show, like we are going to do now, that any n linearly independent vectors for an n-dimensional space is a basis, right? So how do we see this? So let E1, E2, E3, so on up to En be some arbitrary set of n. The key point is that they are all linearly independent vectors of an n-dimensional vector space. Now, what do we have to show? We have to show that we should be able to expand. So this set of vectors is going to have to span the space, right? Because they are already linearly independent. If they manage to span the space, they are a legitimate basis. Now consider any vector x which is an element of V. We must show that this vector can be expanded in terms of this. So let us consider, the set of n plus 1 vectors, right? You have E1, E2, E3 all the way up to n, and let's put also x into this box. And we have a set of n plus 1 vectors and in an n-dimensional space. But we have just managed to show in the previous result that any n plus 1 vectors, right, have to be linearly dependent in an n-dimensional space, right? Now that means that we'll be able to find these coefficients eta 1, eta 2, all the way up to eta n plus 1, such that non-trivial coefficients, such that the sum of this object is going to be 0, eta 1 e1 plus eta 2 e2, so on up to eta n plus 1x is equal to 0. Now let us, all we have to do is show that eta n plus 1 is not equal to 0, and then we're done, as you will see in a moment. Now because, why is eta n plus 1 not equal to 0? Because if eta n plus 1 equal to 0, then it means that eta 1 e1 plus eta 2 e2 all the way up to eta n en is equal to 0, right? And also eta 1, eta 2, eta n are non-trivial coefficients. If this is true, then this will imply that the set e1, e2 all the way up to en itself is linearly dependent. But that's not true. We are given that e1 to en are a set of n linearly independent vectors. Therefore, eta n plus 1 is non-zero. Now, why is this important for us? It's important because we would like to divide throughout by eta n plus 1. Right? If we do this, then we can express x as minus 1 over eta n plus 1 times this eta 1 e1 plus eta 2 e2, so on all the way up to eta n en. Right? So thus we have managed to show that any arbitrary vector in your vector space can be expanded as a linear combination of these n linearly independent vectors. Therefore, this set is a basis, right? So that's one more result which follows directly from the previous result that we described earlier, which in turn followed from ideas from matrices, and all these results are cleverly and intimately linked together. So if you are confused about some of these ideas, you should go back and review some of the ideas from the earlier lectures. That's all for this lecture. Thank you.